Dear colleagues, it is a pleasure on behalf of NT-MDT Spectrum Instruments to welcome you at our webinar, Nanoscale Infrared Microscopy and Spectroscopy. My name is Stanislav Liesman. I am the Director of Software Development and Marketing in our company. So today I'll be the moderator of our webinar. I would like to introduce you our lecturer, Dr. Vyacheslav Polyakov. Vyacheslav is the head of the R&D department. If you have any questions, you can use the GoToWebinar chat tool to submit them, and we will try to also answer as many as possible of them after the webinar, or we'll send you the written answers in the follow-up letter. So, moment, yeah. So Vyacheslav, I think you are online.
All right, ladies and gentlemen, good afternoon. Thank you, Dr. Liesman, for your warm introduction, and you're very welcome to our today's webinar. And our topic is the nanoscale infrared microscopy and spectroscopy. Today we will start with the brief introduction about the AFM technology in general and the possible combination of atomic force microscopy with the optical spectroscopy techniques. Then we will move to the nanoscale infrared microscopy. That is actually the main topic of our today's presentation, and we'll make some conclusions. Right. So just a brief reminder that the history of scanning probe microscopy starts with a scanning tunneling microscope that was actually introduced by Ping and Rotor in 1982, and they then got a Nobel Prize in 1986 for their invention. But the limitation of the scanning probe microscopy was obvious from the very beginning, and from actually the invention of the method, because the STM can be plots just to conductive samples, and that is why the same group was introducing the atomic force microscope in 1986, and actually last year it was the 30 years anniversary since Pinning, White, and Gerber introduced the first publication about the atomic force microscope. Well, by the way, the idea that the surface can be investigated by touching it with a sharp tip is quite simple, and even in the last century in Germany, it was a German engineer, Schmalz, who in 1929 made a very simple prototype of atomic force microscope, where he used actually the sharp tip, where he used the light source and the photographic film, and he was organizing the scanning of the sample by this tip, and then this photographic film was then this photography film, so actually he was able to get the resolution, to get the magnification of the optical resolution about 1,000 times or even 10,000 times. And in the invention of the technique, a lot of methods and technologies were developed, not just to measure the sample, but also to measure its electrical properties, also to measure its magnetical properties, to measure the nanomechanical properties of the samples. And then actually in 1988, we were the first commercial company who introduced of IFM and IFM Raman system. So since that time, the technology moved forward a lot, and the special idea of combining the optical techniques with the atomic force microscopy also was developed in a quite a large-scale area. And in general, there are three ways how to improve the optical resolution by using the atomic force microscope. The first way is to use a tip-enhanced near-field optical microscopy, when we have the light localization and enhancement by localized surface plasmon. This is the physical phenomena that can be applied to a quite variety of samples, but it needs the resonant enhancement of the optical light. The second way where we will be focused today is the apertureless scattering scanning near field optical microscopy, where there is just a tip of the atomic force microscope and there is some light, in our case, near the spectral region, and the backscattered light is then by interferometer or by other. This is the way where there is no any resonance, but the as we will see, the technique is determined by the curvative radius of the probe. And there is a third way that we will not be focused today, but just to mention about the use of a special aperture scanning field microscopy. The probes using the just to decrease the point of interaction between the light and the sample allows to get a spatial resolution that is lower than the wavelengths, and it can be down to about 100 nanometers. So from the hardware point of view, to make these experiments, it is important, first of all, to provide the optical access from any possible directions within the instrument. So there is a sample and the AFM probe, and we need to give to the light the way from top, from the bottom, and from the side. And we need to be able to detect the scattered or reflected or transparent light in different wavelengths, in different spectral ranges, by different techniques and by different types. And even if we, this is an example of the polystyrene with polyvinyl acetate blend, big film on the ATO glass. Using the IFM, we can measure the height and, for example, the surface potential of this sample. The surface potential of this sample. But once we also add the optical techniques like Raman mapping, we can get the Raman map pin on the polyvinyl acetate or polystyrene wavelengths, and we can then decide what is the what component of this blend is the polyvinyl acetate and polystyrene. So we get some elements of the chemical analysis. And this is good, but actually the goal is not just to make the not just to combine two separate instruments in one machine, but to improve the spatial resolution of the optical techniques by using the atomic force microscopes. And the first way, as it was shown, is actually the tip-enhanced Raman scattering that is shown on the, especially on the carbon type of samples. It was demonstrated that this technique is quite promising and gets a very good spatial resolution, and down to 10 nanometers. And we actually were the first company, the first IFM commercial company that introduced the commercial instrument for it. And actually there are a lot of publications, more than 50 publications with the test results made on different samples. And all these results gotten using different tips, using different IFM feedback regimes like non-contact, contact, hybrid mode, tunnel mode, shear force tuning work, using different illumination and detection geometry on the different wavelengths and on the different type of samples. But for some type of samples, this regime was not actually given a good appropriate results, and this was one of the motivations why we moved to the actually apertureless scanning near field optical. and we'll be focused on this topic today. So the idea is quite simple. Once we have the sample, and once we have the tip, and there is an illumination of infrared light to the region of interaction between the tip and the sample, the scattered electric field is, of course, proportional to the field that is to the accident field. And what's important is that this dependence is strictly non-linear in terms of the dependence between the distance between the sample and the probe. This means that once we have the oscillating AFM probe, and once it is in a so-called taping mode or semi-contact regime of interaction between the probe and the sample, we then can analyze the scattered light. And using this scattered light, we then can understand the contrast of the complex dielectric permittivity of the sample that is actually corresponds and refers to its chemical composition and to its actual physical structure. Of course, there are not too much light going from the very localized area of interaction of AFM tip with the sample. That's why we need to amplify it. And to amplify it, we use the classical way. We use the microscope interferometer that is supposed to amplify the scattered light, backscattered light between the probe and the sample. And then the output signal of the system, that is on the detector, is going to be analyzed on the doubled or tripled frequency of cantilever oscillations. Actually, it is worth to mention that there are two possible approaches to combine the infrared techniques with the AFM. And the approach that I have just described refers to scanning near-field optical microscopy. The second approach is to measure the mechanical response of the cantilever without using any optical techniques. So when one just illuminate the area of interaction of cantilever and the sample with the infrared light, and then measure the spectrum. And it is reported that in this regime, it is possible to measure the spectrums of the samples, but there are actually some disadvantages of this mode because the thermal expansion works well just for a limited range of the sample thickness. So that's why we use the scattering s-SNOM regime, and this regime is actually realized in our Integra Nano IR system. That is the system that is specially designed for these infrared measurements. In the left part of the slide, this is the picture of the system and how it looks like. The system actually consists of two parts. First, the AFM, and second, the microscope interferometer, its optical part that allows to measure the backscattered light, then to analyze it, and then to get the data about the complex dielectric permittivity of the sample. This is how the system looks like. In the top left side, this is the picture of the system, the photo of it. In the right part, there is the specially developed measuring head that allows the optical access for either infrared objective or for the parabolic mirror, and it depends on the applications. Once we, for example, work on the single wavelengths, the infrared objective is more preferable, but once we use the different wavelengths, the parabolic mirror is better. And we now move to some examples of its application. So in our setup, we use the infrared laser of 10.6 micron wavelengths. Then that we transfer it to the parabolic mirror and focus that parabolic mirror to the area of interaction of the probe and the sample. And the backscattered light is then analyzed with a microscope interferometer. Well, the initial tests were done on the quite simple sample, like for example, calibration grating that consists of the silicon substrate with the silicon oxide squares made on it. And in the left picture, we can see the topography of the sample, and on the right picture, we can see the optical response, scattering s-SNOM response. Well, first of all, because these two materials, chemically different materials, one is silicon and the other is the silicon oxide, we can see the contrast, and using this test sample, we then can make some conclusions about the spatial resolution of the technique, about the spatial resolution of the technique. And in this case, it is about 20 nanometers. And another example is it was mentioned already, is the mix of polystyrene with polyvinyl acetate polymer blend that is placed on the ATO glass. In the left part of the slide, there is the topography image of this blend, and we can see that this is actually the two-component material. We can see the matrix, and we can see some round shape including into this matrix. Some of them are higher than the topography, the average topography of the sample, and some of them are lower, but suppose that we don't know who is the polystyrene and who is the polyvinyl acetate. But infrared contrast in absorption image gives us the clear response. All these includings are still on the same color and they're still bright in this image, and then we can get the information about actually the chemical composition of the sample. This is, by the way, that it's interesting that the scale of these scan images is 5 microns. That is 2 times smaller than the wavelengths of the used laser. But the spatial resolution is of course much lower than the wavelengths, so we are far beyond the diffraction limit. This is in XY plane, but what's happening when we work in vertical direction? This example is the ultra-thin film of oligodiaphragm monolayers on silicon. In the left part, there is topography, and in the central part, there is an infrared contrast. And one can see that each of 5 3.4 nanometer steps are clearly resolved in the image, in the optical contrast. So this means that in vertical direction, we can demonstrate the spatial resolution that is better than lambda divided by 1000. Another example is a high temperature IFM and s-SNOM measurements on a phase changing materials. Vanadium oxide is a well-known material that is changing its properties from the insulating to conductive stage within a quite narrow temperature band. And in this picture, there is an overlay of the optical response, of the phase optical response, and the topography of the samples measured at 2 different temperatures, at 27 degrees Celsius and at 67 Celsius degrees. And one can see that there are some yellow marked areas in the pictures that with the growing of the temperature becomes the unique structure, and that then gives the in general the microscopic conductivity of this. Another example is the measurement of the thermoplastic vulcanizate. This is a sample that where the carbon nanoparticles are induced into the thermoplastic vulcanizate, and we can hardly see them in the height image, but in the infrared picture, in the infrared contrast, we can clearly see that these bright points, that actually correspond to these carbon nanoparticles introduced within the sample. And it is, by the way, confirmed by another techniques, for example, capacitance microscopy, where because of different dielectric coefficients of these materials, we can see this bright parts in the image. Well, all the images mentioned above were measured in so-called two-pass modes, when you first measure the reflection and then measure the absorption contrast of the sample. And to go from the first measurement to another, one needs to move the base mirror of the microscope interferometer to change the optical phase of the incident light, first of all. And secondly, in all these images, we need the reference to understand where where the initial phase is. For example, if it is the polymer blend of polystyrene with polyvinyl acetate, it is preferable to have within the scan range to have the reference to ATO glass that is supposed to be 100% reflective on this wavelength, or in other cases to have some silicon parts, to have some silicon substrate that is supposed to be transparent on this wavelength. And this is a disadvantage of the technique. Well, another way is to have the reference mirror oscillating that our colleagues from other companies are doing, to have this mirror oscillating and constantly digitalize the output signal from the bolometer, from the detector of the interferometer, and then to analyze it mathematically, optical amplitude and optical phase of the backscattered light. We proposed another approach that we call the phase-locked homodyne mode. We have the light source. In our case, this is an infrared CO2 laser on 10.6 microns. That then goes through the attenuator to the microscope interferometer, and then goes to the area of interaction of probe and the sample. The probe oscillates on its resonant frequency, and there is a first feedback system that, as in the usual taping mode or semi-contact mode of IFM, the first feedback just holds the probe, hold the amplitude of the probe oscillation constantly, and this is just a regular taping or semi-contact regime. But at the same time, on the second harmonic, on the doubled frequency, not on the second harmonic, but on the doubled frequency of the ventilator, we have the output signal of the bolometer that is then again locked in with a third locking amplifier, and this is used as a feedback signal to keep the optical phase of backscattered light constant. As the result, we can automatically get, without any need of reference in the sample, or without any need of additional adjustments of two-pass, or any need of using two-pass regimes, we can get the contrast of optical amplitude and the optical phase of the backscattered light. And this is an example of how it works. In this picture, the sample consists actually of two silicon gratings. The base part of the grating is the N-type silicon, and these two parts, so these two gratings are then, well, they are covered by silicon oxide and then glued together on their cross section, and on the cross section, and in the FM topography image, well, we can see that this is the structure, and on the s-SNOM signal, we can see on the amplitude signal, the optical amplitude corresponds to the real part of the dielectric permittivity of the sample. That there are actually different, chemically different materials. The silicon has its own dielectric permittivity, the oxide its own, and the band and the gluten has its own dielectric permittivity. But in the optical phase signal, in the s-SNOM signal, one can see the bright area that corresponds to the actually highly doped p-type silicon areas. So one can determine with this technique the level, not the level, but the difference in the dopant level of the semiconductors. And these results are actually supported and confirmed by the results of the scanning capacitance microscopy DC by DV that are presented in the bottom part of the slide, especially on the CV curves. One can see that in the p-doped and n-doped areas, these curves have a different behavior, and now these two techniques, s-SNOM and the capacitance microscopy, are actually complementary to each other, because s-SNOM is highly sensitive for the higher Curie concentrations, and the capacitance microscopy is highly sensitive for lower Curie concentration. Another example is the semiconductor structure. This is the MOS transistor made on the same. The results are made on the same wavelengths. One can see on the topography that this is actually just the topography of this sample, and on the scattering SNOM signals on amplitude and phase, we can definitely resolve the differently doped areas of it. Well, this is the examples of scattering SNOM that scattering SNOM that that we measured in one pass mode using the special technique that we have developed by keeping the special feedback to keep the optical phase of the scattered light constant. In the beginning of the presentation, we mentioned that there is a second approach to the IFM infrared measurements that refers to the thermal expansion of the sample and to the measurement not of the optical response of the sample, but of the mechanical response of the cantilever. And this is one of examples. This is the mix of the polystyrene with polyvinyl acetate, and still on the same wavelengths, 10.8 micrometers. We use the modulated laser source with the frequency of about 20 kilohertz, and in the left part of the slide there is the topography of the sample, and in the right part of the slide we can see the thermal expansion contrast. We can see the polystyrene, that is actually the matrix here, expands more than the polyvinyl acetate, and the includings of the polystyrene within the round-shaped areas are also demonstrate the good response. This is another example, just to zoom in of the same sample that also demonstrates that we can make these capabilities, but these techniques that measures the mechanical response of the cantilever and the thermal expansions, they're quite limited in both the type of samples and the sample thickness. So we are now going to conclusions. First of all, it's definitely the combination of atomic force microscopy with infrared microscopy or spectroscopy opens a wide perspective way for chemical analysis of different type of samples with nanometer spatial resolution. We are in NT-MDT spectrum instruments, and we are the FM company, and we have the low drift FM and low noise FM with wide range of IFM techniques, and all these techniques, including combinations of the atomic force microscopy with the different optical techniques, are complementary to each other, and they allow to characterize the sample from the point of view of its different properties. Well, and actually we offer the only solution that is able to integrate scanning near-field optical microscopy in infrared range and Raman microscopy in the same system. Once again, ladies and gentlemen, thank you so much for attending this webinar, and your questions are very welcome.
Okay, thank you, Vyacheslav. So yes, we got a couple of questions here. So let's start with this one. Question is, how thin should be the sample for s-SNOM and AFM IR modes?
Well, in scattering SNOM regime, we do not actually have limitations in the sample thickness. If it is the optical response from the sample, and we can measure the optical amplitude and optical phase of the backscattered light that corresponds to its dielectric permittivity, we can do it on both thin and thick samples. In fMIR modes, where we measure the mechanical response, there is a limitation. The sample cannot be too thin, because it was shown in the one of the slides, this ligate-FN monolayers, for example, they are too thin to actually demonstrate the thermal expansion. Mode, but in the scattering SNOM regime mode, we can clearly see the contrast.
Okay, thank you. The next question, is it possible to use my own infrared source?
Well, it depends on what kind of infrared source it is. Actually, for scattering SNOM regime, we need the constant wavelengths, the constant light source. For the AFM infrared regime, where the mechanical response is measured, it can be, the pulse laser can be used. So it actually depends on what kind of sources existing.
Okay, we are getting more and more questions here. That's nice. We'll try to manage to do as many as possible today. There is a question. Could you go to the sorry? Could you go to slide on how you minimize the thermal drift?
Yes, thanks for this question. This is a good question. Well, I'm not sure what slide do you mean, but probably this one or whatever. Well, actually, the minimization of the thermal drift is one of the very important issues in atomic force microscopy, and its different application and combinations with the optical techniques. Well, first of all, our system that is actually shown here is made from titanium, and it is it has a special axial symmetry that allows to minimize thermal drift of the whole system and to improve the stability. The second point is that all optical part of the system also needs to be very stable in terms of the both thermal drifts and in terms of just mechanical vibrations. And this is how it works.
Okay, from my side, I would also to add that the good quality of AFM, the low thermal drift and the low noise is a really important point in the combination of AFM together with other techniques. So in this case, we did really work on this good solution.
Yes. Thank you, Stanislav. This is very good point, because once we combine different techniques, and once we are going to get the actually the good spatial resolution, we have to work on the boundary of the signals, and we have to work with the signals that are quite on the noise level. And in this kind of systems, all components, including the optical components, optical parts, and including the AFM, should be very optimized in terms of the stability and in terms of in terms of their noise characteristics.
Okay, some technical question. How do you align the infrared beam to the tip?
Well, first of all, there is a visible. This is a good slide that is right now open in the presentation. First of all, there is a visible laser that is previously aligned with the infrared laser, and this visible red laser is going to the tip and is used for initial alignment of the whole optical system. And then once we are going to scan, we are making this parabolic mirror is placed on the piezo stage platform that allows to scan it in X, Y, and Z direction. And then we make a scanning by this mirror, and then we get a hotspot and align the accident beam with the cantilever.
Okay, one more question. You always show a parabolic mirror focusing on the tip in the schemes. However, the photos shows a transmission objective. Is the paraboloid option commercial option?
Yes, just we have two options. First option is when we use the objective, and the second option when we have a parabolic mirror. For example, in this system that is shown in this picture, the objective is used. In our own system that is placed in our lab, the parabolic mirror is used.
Okay, so some AFM related question. What is the noise level of your AFM part, AFM head?
The AFM head itself, the optical beam detection scheme, has a noise level of about 25 femtometers per square root from hertz. Now, once it is in the the cantilever is in contact with the sample, we have the noise level of about 0.3 angstroms in the 10 till 1000 hertz range, frequency range.
Okay, I see that our attendees had some experience with such systems, so very specific but interesting questions. How do you handle the AFM laser with the infrared source for a simultaneously image? Are there any noises? I think this question is related to the cross noises.
You mean the cross noises between the AFM between the AFM laser and the infrared laser that's used for scattering s-SNOM signal? Well, first of all, the detector, the photodiode detector that's used to in optical beam deflection scheme is in the other spectral region, and it doesn't work with this with this spectral range, and correspondingly that does not feel it. And the second point is that, well, actually, if we would work in the scattering s-SNOM mode on the first harmonic of the cantilever oscillation, we actually could use this, and we can use this microscope interferometer as the optical beam detection setup. But the principal idea here is that we use the double frequency or triple frequency to get the nonlinear response, optical response of interaction between the sample and the probe.
Okay, next question. Is it necessary to use CEW? I think it's continuous wave operation mode for s-SNOM, or pulse mode is also acceptable?
Well, for scattering s-SNOM, the continuous wavelength mode is required.
Okay. Yeah, and you showed several images in your presentation, and there is a question: what are the physical meaning of amplitude and phase signals in s-SNOM mode?
Well, actually this is the amplitude and the optical phase of the backscattered light, and the physical meaning is the following: these two components corresponds to the dielectric permittivity of the sample. The amplitude of scattering SNOM signal corresponds to the dielectric permittivity of the sample, the classical one, and the real part of the complex dielectric permittivity. And the optical phase corresponds to the complex part of the dielectric permittivity of the sample that refers to the well, actually that refers finally to the, for example, the chemical composition of the structure.
Okay, next question. Do you have the tuning fork AFM function in your system?
Yes, we do.
And I guess there are different types of tuning forks. So which type of tuning forks you can use? Vertical and
yeah, well, we can use it both vertical and the shear force tuning fork system.
okay, and one more question. Could you measure infrared spectra with your system?
Yes, we definitely can. Just in our home, in our laboratory system, we have the laser with the fixed wavelength. This is a CO2 laser, but the whole system is designed to be able to operate in the spectral range from 3 to 12 microns wavelengths, and actually it can be expanded up to 20 microns wavelengths.
Okay, Vyacheslav, thank you very much. I think for further questions we will because they are appearing really high speed, we will send the answers in follow-up letters. So I would like to say thank you to all our attendees and see you on our next online and offline events. And after the webinar is finished, you will see a small questionnaire, like 2 questions. So it will be very kind of you if you will answer them to help us to improve our further events. So thank you very much, and see you next time.